In this video, we are going to minimize the cost function we looked at in the last video, but using Lagrange multipliers. So this is example 2, which we will now do with Lagrange multipliers. In the last video, we talked about how we could set that up by substituting our constraint into the objective. So recall that the example was this question where we're designing this rectangular box drawer that's open on the top, so it's missing the top side. And the front of this drawer costs 5 cents per square inch. The material for all the other sides costs 3 cents per square inch. And we were given that the drawer's volume was 1,000 cubic inches. And in the last video, we drew a picture of this shape. We assigned some variables to the different side lengths. And we set up our objective equation, which was the cost. That was the thing that we wanted to minimize. And we set up a constraint equation, which was the given volume. It told us the volume was 1,000. So again, key idea there was, remember, objective is an equation for the thing that we wanted to maximize or minimize, which in this question was the cost. We wanted to build the cheapest possible drawer. All right, so now I want to return to where we were at the start of this video. I've written down my objective equation. I've written down the constraint equation from the last video. So remember that when we do Lagrange multipliers, our objective, we call this f. And the constraint, we rearrange all the terms onto one side to get the other side equal to 0. So we'll get x, y, z minus 1,000 equals 0. And when we do that, this function that we end up with, we call it g. So now we are ready to construct what we called the Lagrangian function. Lagrangian function just means the function that we use when we do Lagrange multipliers. So recall we call that L for Lagrangian. There's going to be 3 variables that this is in terms of now. There's an x, a y, and a z. X, y, and z. And the formula for it, recall, is f. So we start with f, 8xz plus 6yz plus 3xy. So we're starting with f. And then we subtract lambda times the function g. So we got to do minus lambda times g, which was xyz minus 1,000. So g is this portion right here. All right, so now if I simplify and I distribute the lambda, this is going to give me minus lambda xyz plus 1,000, one more 0, lambda. Okay, so we constructed our Lagrangian function. Now we want to find the critical points of this. So we are going to need to take some partial derivatives. Lx, set that equal to 0. Set Ly equal to 0. And Lz, because there's 3 variables this is in terms of. And taking these partial derivatives now, the partial with respect to x of the first term is az. For the next term it's 0 because there's no x's in it. For the third term, it'll be plus 3y. For this minus lambda xyz, we'll get minus lambda yz, and then 0 for that last term because there's no x's in it. Set this equal to 0 because we want to find critical points. And now I'll do the partial with respect to y. First term, that partial is 0. The next term, that partial is 6z. The third term, it's going to be plus 3x. This fourth term, with this minus lambda xyz, I'll get minus lambda xz equals 0. And then partial with respect to z, when I do it for the first term, I'll get 8x. For the next term, I'll get plus 6y. For the third term, I'll get 0 because there's no z's in it. For the fourth term, we will get minus lambda xy. The last term has no z's, so that partial is 0. And this equals 0. Alrighty, so we have these partial derivatives, and this is giving us 1, 2, 3 equations so far. but we have 4 unknowns. We don't know x, y, or lambda. So we need a 4th equation to be able to solve for this. And recall that comes from the constraint. So the constraint was the fact that x, y, z equals 1,000. Okay, if I wanted to move the 1,000 to the left so that it equals 0, that would be fine as well. It's just that constraint equation. So we need to solve this system of equations now. And I want you to pause the video to try this on your own first. So pause it for about 4 minutes to really try to solve the system on your own first. 4, 3, 2, 1, pause the video. Pause it for about 4 minutes to try to solve the system. This is often where a lot of the work of a Lagrange problem lies, so it's especially important to get practice with this process. All right, so hopefully you've done that. Hopefully you paused it and tried to solve this for about 4 minutes. So there's a few different ways that we could approach this. One thing that I could do is, if I look at the first equation, in fact, if I look at all these equations, they all look somewhat similar in their format. So I'm going to focus on the first 2 equations first, and I'm going to isolate lambda in both of those equations. So I'll rewrite the first equation as, let's put it in black, as 8z plus 3y equals lambda yz. I'm going to do the same thing in the second equation and move the lambda term over to get 6z plus 3x equals lambda xz. And then in both of these equations, I'm going to isolate lambda. So in the first one, I would get 8z plus 3y divided by yz equals lambda. And in the second one, lambda. The second one, I get 6z plus 3x divided by xz equals lambda. So I have this expression for what lambda equals from the first equation, and I have the second expression for what lambda equals from the second equation. And the nice thing about isolating the lambdas in these 2 equations lets me now set them equal to each other. So we get 8z plus 3y over yz equals 6z plus 3x over xz. So we've set the first expression we got for lambda, highlighted in yellow, equal to the second expression we got for lambda, which is highlighted in blue. So I need to keep working with this equation. So I can get rid of the fractions if I multiply both sides by x, y, z. So let's multiply both sides by that. And doing that, it's going to cancel out this denominator and leave me with x. Let me write that a bit better. Okay, it'll cancel out the y and the z, but it'll leave the x. On the other side, it'll cancel out the x and the z on the bottom. Cancel out the x, cancel out the z, and leave the y. So on the left, the x survives. On the right, the y survives. And if I distribute x to the terms in the numerator, we'll get 8xz plus 3xy. On the right, if I distribute the y, we'll get 6yz plus 3xy. And there's more cancellation. I noticed the 3xy's cancel on both sides. So I get 8xz equals 6yz. At this point, it is really tempting to say, wait, there's a z on the left, a z on the right. Can I just divide both sides by z to get rid of it? And we need to be careful there. That is actually a major rule break from algebra. We do not want to divide both sides of an equation by a variable if it can cancel it out. So I'm going to say, do not divide and cancel. Do not divide and cancel a variable, because what if the variable is 0? If the variable was 0, then you'd be dividing both sides by 0, which would make your fractions undefined. The other thing that we notice about this, so I'm going to put a little box around this, is that if z was to equal 0 here, and I were to plug it into both sides, it actually works. It makes both sides of this equation the same. So z equals 0 is actually part of a solution. And if I divide both sides by z, I would lose that solution because the z would go away. So the moral is, I never want to divide both sides of an equation by a variable and cancel away that variable, because I could end up losing the solution. Okay, instead, let's move all the terms to one side. 8xz minus 6yz equals 0. And then factor. I notice that 2 and z are common. And if I factor that out, I'm left with 4x minus 3y equals 0. And from this, we get two possibilities. So once it's factored from this first factor, I would get that z equals 0. From the second factor, the 4x minus 3y, we get that 4x equals 3y. So I want to zoom it out so I can look back at my 4 equations. Z equals 0 is impossible. There's some issue with z equals 0 and one of my equations. Pause the video for about 30 seconds, maybe 45 seconds, 30 seconds, 30 to 45, and see if you can identify what is the issue with z equals 0. What makes it impossible? 4, 3, 2, 1, pause the video. Pause it for 30 seconds to really think about why. All right, so hopefully you've done that. Hopefully you paused it to think about why. That's impossible because of the fourth equation. The fourth equation says, so it's impossible since the fourth equation says x times y times z needs to be equal to 1,000. And if I were to plug 0 in for the z, the left-hand side would become 0. It wouldn't be 1,000. So z equals 0 ends up not being a possibility. But I do need to be careful about this thing. In general, when I do Lagrange problems, there could definitely be a situation where a situation like this, where z was 0, would end up giving me an answer, and I would need to consider it. It just, here I got a little bit lucky, and it didn't satisfy that last equation. So it cuts down our work. Okay, so I do have this other scenario, though, where 4x equals 3y, and I got to keep running with that, because maybe this will give me some answers. So I haven't worked with my third equation. From the third equation, I'm going to zoom out one more time. If I rearrange it to isolate the lambda, I would end up getting 8x plus 6y over xy equals lambda. So I've done a couple of steps at once there, but I've just isolated the lambda. And I'm going to highlight this one in green, just because we are in this pattern of every single time we isolated the lambda, I've been highlighting it just so it pops a little bit more. So one thing that you might be thinking is, wait, I just divided both sides by the xy to get this. I divided by variables. So that is actually okay here because we didn't cancel away a variable. So dividing is okay since the variables, I'm just going to abbreviate vars for variables. Variables don't cancel when I divided by this xy. But above, at this step, actually no, the previous step, this step over here, if I had divided both sides by z, the z's would have canceled and that would have been bad. That is the difference. So just like we did before when we set two of these lambda expressions equal, let's set this third lambda expression we got equal to, let's say, the second one that we had above. So if we do that, we would get the 6z plus 3x over xz. That was the blue one. That's going to be equal to the 8x plus 6y over xy. That was the green one. Oh, no, whoops. I want to highlight. That was the green one. Okay, and just like before, I can multiply both sides by xyz to cancel out the denominators and get rid of the fractions. So multiply both sides by xyz, And if I do that, on the left-hand side, I will end up with the x and the z canceling. So z cancels, x cancels, and we still have the y. And y is going to distribute to the terms on the top to give me 6yz plus 3xy. On the right, the x and the y will cancel. Let's put that in red, maybe. X and y cancel, x and y cancel, but we still have the z. So that will give me, when z distributes, we'll get z equals 8xz plus 6yz. And that's nice because the 6yz cancels. So we got that 3xy equals 8xz. And just like before, I don't want to divide both sides by x to cancel it away, because I might lose a solution if I divide and cancel a variable. Instead, anytime I'm tempted to do that, move all the terms to one side, 3xy minus 8xz equals 0, and then factor. I can factor out an x, and I'm left with 3y minus 8z equals 0. So from the first factor, I get that x equals 0. From the second factor, I get that 3y equals 8z. And just like before, x equals 0 in this problem is impossible, since our constraint equation said x times y times z needs to be equal to 1,000. But if x was 0, it would make the left-hand side become 0. It wouldn't be 1,000. All right, so we do have this equation, 3y equals 8z, to work with. At this point, there are two equations like that we know that we've gotten. The first was 4x equals 3y, and the other one that we just got now is 3y equals 8z. So let's isolate one of the variables in each. If I isolate the x in the first equation, I get x equals 3/4 y. And if I isolate z in the other equation, we'll get 3/8 y equals z. And what I can do now is take these and substitute them into our constraint equation. X times y times z equals 1,000. Okay, so the nice thing about isolating for x and z in these equations is when I plug these in, my only variable is going to end up being y, and that is great for us. So if I plug in the x and the z, we get x is 3/4 y times the y, and z is 3/8 y equals 1,000. So 3/4 times 3/8 gives me 9/32. And then we get y cubed equals 1,000. And I can isolate the y cubed now. We get y cubed equals 1,000 times, and I'd have to multiply over the reciprocal, 32/9. And multiplying that by 1,000, we will get 32,000/9. So 32,000/9. In fact, let me just make that clearer. 32,000/9. All right, so we know what y is at this point. So let's write it down. We know to get y, I would just cube root both sides. And that would give us y equals the cube root of 32,000/9. And I'll plug this into a calculator and tell you what this is roughly, rounded. But before I do that, let's say what x is and what z is. So if I plug this value of y into this formula for x equals 3/4 y, we'll get x equals 3/4 times this cube root of 32,000/9. Doing that for z, we get z equals 3/8 times that cube root of 32,000/9, and plugging these into a calculator, we get y is about 15 0.2629. X is approximately 11.4471. And Z is approximately 5.7236. And the units of length that we were using are inches. So those are the dimensions. And that's what part A of this question was asking us. So this was the answer to A. It wanted the dimensions of this drawer that give us the cheapest possible drawer. And remember one of the things that we commented about Lagrange when we first introduced this method, that when we go through this process and we find these points, in this case we ended up with just one point, if we end up with just one point, we are just going to assume that it's the point that we wanted. That if we wanted to maximize our function, that this maximizes it. Or if we wanted to minimize our function, that one point will minimize it. All right, so now that we have those dimensions, let's answer part B. So part B, remember, was asking, well, what is the cost now? What is that cheapest cost? So to answer this, remember what our cost function was. And to find the cost, I would plug in the x, the y, and the z into this function. And if we did that, we end up getting that our cost is approximately 1572.44, if I round it to 2 decimal places. The units of cost in this problem were cents. If I put that in dollars, I would divide this by 100. That would move the decimal 2 spots to the left. And we'd get this is 15.72, if I rounded it to 2 decimal places. $15.72, or about $15.72. That's the cost of the cheapest possible drawer that we can make. So questions like this are really commonly faced by businesses when they're planning out their packaging for their product. Because a business is interested in knowing what the cheapest possible packaging would be. So it's a very natural question that businesses are interested in. So in the next video, we will do another Lagrange example.